All right,
Nice.
Good time of day, everyone. Welcome to the new MLIR meeting. Today, Alex has a proposal about an interesting dialect and interface for transformation. Alex?
Thanks, Mehdi. So, hi, everyone. I'm Zinenko from Google. I would like to discuss an RFC we posted recently on the forum about transform interfaces. Basically, give some more broader motivation and rationale why we are doing this or why we want to do this and what we want to achieve. That is difficult to put in text, or it would have been too long to be able to read. So I'll start by throwing stuff at you. And if you look at research literature on high-performance computing compilers in the past 10, actually more years, we'll see that there are a lot of works that introduce a notion of a schedule. So probably the most famous one is Halide, which separated the compute representation where you express what you want to compute from the schedule representation where you express how do you want this compute to be executed. And there are many more things. There is TVM, which is partially based on Halide, which introduces metaprogrammable from Python schedules that are more expressive than Halides. There is our work with Nicholas and others on TC, which has some sort of schedules. There is FireIron from NVIDIA, which also has a sort of scheduling API or language for data motion on GPUs. And there are many more. And if we look more into history, it's not like the last decade. Like the one I'm aware of, there is a long history of such schedule or declarative transformations in the polyhedral compilation community. And I found one from 1991. And basically these transformations we know quite well and we know how to do. And there is a lot of work that demonstrates that we need very precise and specific control over the transformations if we really want to achieve high performance code generated from a tool. It doesn't mean we don't want to have fully automated process. It doesn't mean we don't want to have semi-automated tunable process, but being able to express these schedules and precisely say we want to transform a part of a program following this recipe is an important part of getting good performance in compilers, according to recent research. So that basically summarizes what I'm trying to say, is there is many things that use these schedules. Schedules allow us to identify a part of a program or properties of parts of a program that we want to transform, and target transformations add those parts specifically, not just blanket transform. Like we don't want to blanket unroll on loops. We don't want to rewrite some higher level operations uniformly in all cases. So we want some finer grain control in addition to what we already have. Such schedules, if they are transformed, if they are represented as some sort of text or code or any other exchange format, essentially allow for what we usually call heuristics to be externalized. So instead of having a hard-coded C++ or TableGen or whatever heuristic that is coded into the compiler, that is written once in the compiler, compiled and shipped, we can actually have these heuristics be separate and have the compiler read them and implement them. So we can actually change the heuristic for the compiler as long as we have the transformations we want at any time. So we can ship the optimization strategy separately from the compiler. So if there is new hardware that comes out, or if there is new combination of basic transformations we know gives better performance, or if we need to specifically optimize something for a particular code. So for example, like ResNet and convolutions have become really, really important in some models. So instead of developing a new compiler or redeveloping a compiler just to have a new heuristic that handles this well, we can just give a heuristic as a sort of transformation recipe to the compiler that is able to interpret it. And finally, and perhaps most importantly for me in research, is that such reified schedules can be easily generated via auto-tuning. So they're essentially text, or better IR, we'll get to that, but they're text or code. And there's plenty of tools that are able to generate these with some level of automation. So we can actually have tools that generate these heuristics and communicate with the compiler without having the tools actually in the compiler or deeply understand what the compiler does. So the goal of what we are trying to propose here is have a mechanism that is similar to these schedules in MLIR that scales to what MLIR usually does. So we want it to work in presence of custom and out-of-tree dialects, which can have their ops, which can have their transforms. It should also work with generic transforms, I presume, that themselves can be implemented for interfaces. And we obviously want to reuse as much as possible from MLIR and be minimally intrusive. Ideally non-intrusive, we'll get to that, but minimally intrusive in the infrastructure. So we don't want to replace any of the things that exist. We want to complement them and to enable the kind of work research people keep doing on more advanced targeting of transformations and scheduling languages. So there are some challenges if we just try to implement this using what we have, namely passes, rewrites, and so on. And one of the biggest things that are challenging is how do we chain transformations, so how we communicate information between them. So a very common example that I've seen in loop-based code generation is when you want to say something, I want to find all loops that I know have either an undefined or sufficiently large size. I want to tile them and I want to unroll them so the vectorizer kicks in. And this then unroll the resulting loops is really difficult to explain unless you build a specific tile and unroll transformation. Because we cannot attach this as an attribute. Attributes are unstable. We don't want attributes pertaining to transformations to persist, and there is no guarantee that they will persist in the IR. And the only way to say then is to actually fuse these things into a single transform. But then we actually want transforms to compose and combine. So we'll need to do tile and unroll. We'll also need tile and path, tile and tile again, and unroll, and promote to GPU, and path, and something else. So these things need to combine and compose, and it is quite challenging to compose them when they run as separate passes or separate transformations. Other are more like of things we want to have, but they're less important in my opinion. But still, they're useful, and they're useful for reasoning about transformations. So possibility to look at the transformation, analyze it, simplify it sometimes. For example, if we generate these transformations, we can say, well, tiling by 0 is actually not helpful because it's a null. So is unrolling by 1, and some other transformations may just cancel each other. So in anything automated that generates its things, being able to analyze and simplify is important. So is being able to store and ship this. And finally, well, that kind of comes with MLIR. We really want an open set of transformations and rules, as opposed to just having a heuristic or a set of heuristics that can be parameterized, but cannot really be targeted. If we really want to push this, we can have a heuristic that is basically parameterized by IR as a string operand, and we just parse that IR and do the same thing we're trying to propose here at a distance. So what we would like to see happen is these transformations being expressed as IR, because we are in MLIR. When we need to do something, the usual solution is to design a dialect or have interfaces or BOS. So here it's actually BOS. And we want to express transformations as IR, and here's a simple example of how it could look like. So here we say there is a hypothetical transform X form for brevity dialect that first contains a matcher part, and we already have a good infrastructure for matching with PDL. So we can basically use the PDL dialect to express what kind of operations we want to target in our transformations. So PDL can express basically anything. It can hook back to C++ if you wanted to. So we can find the operations we want to transform the same way we would do it for usual pattern rewrites. But then we can say we want to transform these operations declaratively by saying, let's find some loops, for example. I like loops. It's most of my background. And let's style them. So instead of combine this in transformation, we would express this as, hey, PDL, go match this thing, give me a list of loops that correspond to my criteria, and then the transform thing says affine tile, which will actually correspond to a tiling transformation. So in this, we have SSA values that I call handles and that correspond to operations in the actual IR we are transforming. Most transformations take handles of the operations they are going to transform and may produce new handles so that we can actually change this thing. In this example, we tile twice, which is quite common. Sometimes we tile up to 3 times based on the memory hierarchy. So here we tile with a specific site, and then we tile again the results of tiling. So we clearly say that we want to chain one transformation on another. We have an operation that corresponds to a transform, and this entire thing could work by having some sort of interpreter infrastructure. I'm not sure interpreter is the right word, but something that reads this and calls to the actual transformation, which may be a pattern, which may be a path, which may be basically any C++ code we want. What's also interesting here is that all the transformation properties and all the configuration of a particular transformation can be provided as attributes of this operation. So here I provide tile sizes, but it can really be anything. And what's even more interesting, since it's a dialect, we can start building frontends for this. So we can have meta programming for transformations, or we can start building higher level dialects. So instead of saying, well, tiles and unrolls and vectorize, we can have a higher level transformation. Let's call it a recipe or an expert. Yes, there is a typo. It should be either a 1.0 or 1.1. But yeah, it's just a small typo. The point is that we want to actually change transformations. And then for tiling, it would be like you have one value that corresponds to tile loops or to point loops. Yeah, thanks for catching. So this will be read and understood by something that actually performs the transformation and also keeps track of the things we transform. Then we can have higher level dialects that express more complex transformations that get decomposed, or this thing, if possible, can also be decomposed to, for example, PDL rewrite patterns or any other pattern infrastructure we have in MLIR. There's a question, often the tiling size needs to be adapted to the input size. Is it possible? Yes, it could be possible by expanding this. So if the transformation would accept either symbols or more SSA values. So let's say the match operation would return not only the operation we are trying to transform, but also the operations that define its sizes. We can then pass that handle into the tile operation and use that, for example, to compute tile loop sizes dynamically and to emit code that computes them at runtime, as an example. The main point here is really to express the transformations we want to perform as operations in IR. And I'm really trying to propose a really broad thing that does not limit this to, I just want to do loop transformations or just want to do polyhedral transformations. What I want to do is I want to be able to target transformations at very concrete ops, reusing the matching infra that we already have, and have an unbounded set of transformations that are not very restrictive, so that can be expanded by users as they see fit. So, and yes.
Quick question. How does this compare to building like an AST for the Halide schedule?
To what, sorry?
So your analogy to Halide, I think, is very good and very helpful. How does this, if you go back to the previous slide, it seems like you're expressing roughly an AST for like the Halide schedule DSO. Is this kind of like encode the schedule in the IR? And so it's...
Yeah, it could be seen as that, but I really want to find a way to scale this to any MLIR transformation.
Right, so not being hard-coded to Halide particularly.
Yeah, it's not like Halide is useful, and I assume many people are familiar with loop transformations or loop-like transformations. That's why I'm using tunneling as an example. But this can be like any rewrite you want.
Okay.
And I want this thing to be like, I want this to actually be an interface, and I'll get to there, where the implementation of the interface is entirely up to whoever defines it.
Right. It's not a closed set of ops that are built in. Yeah.
Exactly.
Makes sense. Cool. Thanks.
Yes, so the benefits of this are, well, kind of trying to address the challenges I posed before. So it is reproducible, so we can have the scheduling recipe, store it, it's just IR. We can compute it separately, so we can have, let's say we just keep using whatever heuristics we have right now, but we can in parallel start a very long and expensive process of finding the best possible heuristic, and then we can just plug it in and the compiler keeps working. So it can be pre-computed outside, it can be replayed. So if something goes wrong, we can actually take the script and make the compiler replay it, so we know what exactly failed, and then we can minimize. So anything you can usually do with code, like any debugging minimization strategy, still works. It becomes more verifiable, so you can just use the op verifiers to check some properties, like tile sizes are decreasing if you tile multiple times, or you're only tiling loops or things that look like loops. They can be simplified, so some things are known to be no-ops, some things cancel each other out. And we can do error reporting because it's just IR. So we can say, well, this thing failed when we tried to apply it to the transformation, to this operation, sorry. Yes, Mahesh.
Yeah, I was just looking at the match, whether it solves one of the issues that we've had with, say, linear transforms a while ago. If you have usually you write a match to match an operation, and then when you tile a linear job, it ends up in another linear job. You need to have complicated mechanisms so that the transformed IR doesn't match again. I don't know if the way this transform dialect or interface is being proposed will address that issue where you can, if you have multiple possible places where it could match, if there's a way to prune the matches as well, or is that kind of orthogonal to what's being described here?
It's a good question. It's more of how you write the match. So far, I haven't really thought about this overlapping thing. So it will be like the way my prototype is currently implemented, it will be greedy. So it will take the first match it finds, do the transformation, and then keep matching. Or if there are multiple ops to match, it will match the first one, then go on, ignore the subtree of the IR, go further, try to match more things, so you get a loop. So you get a history.
Okay.
Yeah, but it can also be increased. But I think this should be coordinated with how PDL evolves and what the developments in PDLL are. So there are more interesting things in how the matching is controlled, and that's why I really want to connect to the matching infra we have, so we don't reinvent it. So if there's a way to do best possible match according to some rules, I'm happy to take that.
Sounds good. Thanks.
More questions? Yeah, don't hesitate to ask questions or post them in the chat. Yeah.
Sorry, I'm trying to figure out how to turn the hand off. So if a sequence starts, is it guaranteed to continue? Because I guess the error here is a static error, or is that dynamic?
So it's dynamic because okay, in this case, I think the way I wrote this, it can be checked statically, but it can also be a dynamic error. So there are errors that I would check in verifiers that we know statically are incorrect transforms, but there can also be you have a pattern that just failed because of some reason internal to this pattern. So it will stop the sequence, and the entire sequence in this case will abort. But basically, the sequence itself is yet another operation that implements the transform interface that basically takes the body and dispatches in a sequence and tries to transform unless there's a failure. And I think my next slide is about possible combinators. So
I'll save some questions for later.
Yeah, we can also think about things like let's try a transformation, and if it fails, let's try another one, and if that fails, let's try another one. So if you are familiar with lift and elevate and that line of work, I think there has been a presentation in the ODM a couple of months ago. We can take these combinators and implement them if you wanted to. So we can go all the way functional I'm not sure it's the preferred way because of the cost, but we can do this try or alternative passes. We can basically try adding control flow in the recipes. So going slightly back, the structure of this thing, well, it's more or less straightforward. So we would have a module with what I call a payload IR or compute IR that is being transformed, and another module that describes the transformation. We can nest them into some top-level module, or we can put them next to each other and just have a tool consume two modules, one with the payload IR and another with transform IR. But it's basically making sure the stuff works. There is nothing magical here. I mentioned combinators, so there are things like try this or repeat until the pattern no longer applies, and so on. There is a question, so this is like the pass pipeline on using IR. It can be seen as a pass pipeline, but ultimately this needs to fit into a pass. So the relation to passes so far, to me, it's more like a tool, similarly to what dialect conversion does. So you can call several of these from a pass, but you presumably, like, there is no technical way of restricting somebody from calling another pass pipeline to implement a single transformation. So it kind of adds an extra level of composition into passes, if you want to. Yes, Mahesh.
Yeah, just going back a bit, you said that the way it's structured today, that it's a module and another module. Maybe it can be made a little bit more general, where you can have a mechanism to specify what the top level of you want to start matching on, like you do passes today, where you say this pass runs on a func op, or maybe like get a little bit more fancy, where you can say an op which has this particular symbol or something that can basically decouple the payload status of module. So yeah, it's not load bearing just in it. It's a minor detail, but just pointing it out that we don't need.
Yeah, the important thing here, I think, is that it is proper IR, and we considered for a while an idea of expressing all this as attributes. So we had the project for some time trying to express loop transformations as attributes, and we ended up practically reinventing SSA in attributes. So at which point, let's just have proper IR. So, but yeah, we can absolutely have some pre-pass that annotates, okay, here's the op I want to transform, so I'll just attach an attribute to it, and your matcher is only looking for the attribute. That is also possible. Okay, another possibility that I wanted to highlight is to have typed handles. So we can say we expect the pattern to produce something that looks like a loop. That can be like implementing a loop-like interface or any other constraint, and then dynamically check if the pattern actually did produce this and fail if it didn't. Or if we have these typed handles, we can actually statically check some of the properties. If we try to outline a function, but the handle is actually a loop handle, that's obviously an error. The transformation will never happen. So we can statically report that this recipe is not correct. There are many other things, but basically I'm trying to get the very high-level structure of how to control these things, how to organize, and how to connect this to the rest of the infra. So the tentative proposal is we could have a dialect transform or X-form containing common ops and utilities, and common ops is something like a module that contains all these things, or a func, or like any container type, and probably top-level operations that organize computation, like sequences or loops or alternatives. Diego asks, I guess we could describe, sorry, it disappeared. We could describe conditional transformation, something like SCF if. Yes, indeed, we could describe something. I don't want to overpromise, and I also want to kind of balance the complexity of this thing. So I don't really want to express the entire compiler in IR. I want to have something that lets us control transformation to some extent. So something like, if size is big enough, or if the pattern is matched, is probably within scope, but very long and complex things that are not really expressible as patterns should probably be out of scope. It's a difficult line, but I want this declarative IR thing, but I don't really want to be writing IR all the time. We should leave some place for code as well.
Okay, thanks. Yeah, that makes sense. I guess these conditions could also be part of the matching, I guess. So
yeah, this could be part of the matching, or there can be alternatives, but I would rather consider this, like, let's call it transformation control flow. I would rather consider this on case-by-case basis. So like having an if probably makes sense with maybe some restrictions of like not having nested ifs or like not allowing arbitrary control flow. So I'm trying also not to overblow the complexity to start with, but it's something that could be considered in the future.
okay, thanks.
Okay, so there's a dialect containing these higher, like top-level things, and there's an interface called, for example, transform of interface. And basically, the interface starts by being very simple. It has one function called apply, and it takes a mutable transform state. And apply returns a result, like whether it failed or not. And what transform state contains is basically a mapping between the values, the SSA values in the transform IR, and list of operations they correspond to in the payload IR. And the state basically has two general calls. One lets you establish this mapping, and another lets you query the mapping. In the RFC on the forum, there is also a proposal for extensions and listeners. So how can specific ops get notified when something gets changed? I'll invite you to read that. So there is some further thinking on how things communicate with each other when necessary. But basically, the general interface is quite simple. Here's this apply thing. It can be arbitrarily complex, and we use our best judgment to say if we want that kind of complexity or not. And plus, we can design traits to handle common cases, such as having a single target and single result, or only having handles as operands and only having handles as results, as a way to implement like applies that automatically maps to apply to each or apply to pairs, like any common combination of things. So that's a general idea. Where I definitely would like some help with discussion is how to layer this thing, and any general feedback and any ideas, concerns are also welcome. So basically, layering, it's where it gets complicated. Is if you want this thing to really scale to any dialect and any kind of transformation, yeah, there are two unsatisfactory solutions. One is having the transform dialect depend on all possible dialects that are being transformed, which creates this kind of tight coupling of everything that we really try to fight with by splitting standard and other things. Or we can have every dialect that wants to be transformable depend on transform, which is also suboptimal. So it kind of makes this transform a core IR thing that everybody is supposed to depend on, which might not be desirable as well. So there are other solutions. One is, well, create an additional, like for each dialect X that you have, create a transform X dialect that depends on X, on transform, and on transforms of X, and have that, but it sounds like creating too many dialects is also not a great solution. River mentioned somehow injecting operations into X form. I'm not sure I fully understand how that could work, but that sounds interesting. So, but basically any ideas on how to layer this and how to make sure this works, especially for out-of-tree projects, are highly appreciated. That's all slides I have. So if there are further questions on what you would like to do, please ask them, and we are happy to discuss. Yes, Mahesh, please.
No, just so that I understand, what's the issue with the second approach where you have every dialect that wants to do transformation depend on the transformation dialect? That seems like fairly okay to me, but I might miss details.
Well, it's not as much technical problem as the first one, but it basically makes this a core approach. It's the same as putting this in libIR. And I'm not sure, at least in the short term, I want it to be in libIR. It's more of a complementary way. It's not how people usually write compilers. So usually there's like IR and there are passes, and people understand how passes work. this is something less conventional. So if the decision is, okay, let's put it somewhere in lib interfaces, sure. But I feel like it should be a separable component to start with. I might be wrong, like I don't have any preconceived opinion here. Yeah, just like PDL. Well, yeah, PDL is kind of a dialect. River, you wanted to say something?
Yeah, sorry, I have my hand up still. So I had a few questions, but I won't ask all of them to not monopolize here. One of the big ones I had is, so maybe this is actually two questions, sorry. I guess the greater question is like what the restrictions are on the transformations that are being run, because you had the sequence operation, which is failable midway, but is it something you have to roll back from? And kind of semi-related to that is, what are the exact restrictions that you're placing on the transformations that are being run here? Like, you had a listener's question mark, but is that a requirement of the system if sequences can fail, but the pass can continue? I don't know if anything there.
Yeah, so I kind of shrugged it away and said, well, the ops, this control flow ops should define what they want to accept, maybe with more interfaces. But basically, yeah, sequences can fail and leave IR in whatever, like valid IR state, same as passes do. So it's more derived from how we do with passes. So a pass can produce IR that is no longer consumable by other passes, but it's still somehow valid. So I think that is the default assumption that I would make. We can also consider transformations can be rolled back, but arguably most of them are not. So it's at the point where we discuss these alternative things that we need to decide. Like if we have this, try this, if it fails, try the other thing, or we actually want the thing we try to be able to, like we want to be able to roll back the thing we try. We can also implement the handling part by, for example, cloning is a part of the IR we're going to transform. So like if we're specifically targeting it to an operation and we know the transformation only touches that operation, maybe it's like backward and forward slice, we can just clone that, transform and go and get back. I'm not saying it's a good solution, but it gives you an easy way to implement something unrollable or undoable to start with, and then we can like borrow from dialect conversion if necessary, or play other tricks depending on what is actually needed. So, and your other question is what transformations we can express. So I'm mostly interested in the transformations that we have in the literature. So it's mostly loop transformations and some higher level things than what we usually express with patterns. So like any loop transforms, anything that looks like polyhedral, some of the linear stuff, some of the TensorFlow fusion stuff. So these are the kind of transformations I'm thinking about. There might be a need to do canonicalization, for example, as an enabling step mostly. And I don't think something like lowering would be a good fit, although I can see like a transformation that lowers everything to LVM.
Okay, so failing here is not like I guess failing past the first one, or maybe even failing the first one. So failing something in this sequence, I guess after the first one is applied, is like a pass failure in a way.
Yeah.
Where it's everything should stop, everything has failed kind of thing. As opposed to like a rewrite failure where it's, oh, I just didn't apply this specific thing. Keep going. Okay. I have other questions, but a bunch of other people have their hands up, so I'll let them go.
Okay. Suraj, you had a question.
Hi, Alex. That's a great talk. And so I'd also put my question on the chat thing, and I wanted to ask. So in the transformation described over here, we are probably talking about compute transformations like tiling that have an implicit memory movement associated with it. You might be dealing with cache locality, trying to optimize that through tiling. But certain architectures may have the compute transformations essentially be entirely about the compute only, and memory movement or transformations being an independent thing. The two need to have aligned together. And maybe I just don't have a mental map of the idea, but perhaps that means you have two independent frames of scheduling artifacts that themselves need to be scheduled in IR. So how would that work?
So I would say this is more on what you want to express. So like what you want, it's up to you as whoever writes this to express this with transformation operations. It would be the same as if you were writing a heuristic in C++ or Python or whatever language, saying, well, I need to express this and that and combine them in my code. You just do it in the IR. So the transformations themselves are common enough so you can reuse them, but how you orchestrate them is like it's up to you. I just want to give the possibility to express these things. I'm not saying, like, I'm not giving a recipe to transform this for a particular architecture. I'm just building the infrastructure for somebody to do that. I'm not sure if that makes sense, but I'm really trying to not define, like, I'm trying to be as open as possible because it's MLIR, and MLIR wants everything to be possible and extensible to the best extent.
Thank you.
Alex Eichenberger, I think, is next.
Yes, thanks. A really nice presentation. I have a question with respect to the infrastructure. In the first slide, you showed how you can basically cascade or making a pipeline of this transformation. Have you made a study to see that that it's flexible enough to represent most important transformation? And for example, what we do is we do tiling and rolling charm. We do buffer. I mean, you buffer specific arrays for a certain duration with copy to a buffer and back from a buffer. And then we often do dynamic versioning. So basically, if the tile size, for example, is full, then we would have one version that where we do a specific unrolling, or if there's another version where the SIMD dimension is full, then we would SIMDize, and then if there's not, we would go back to a scalar. So is this approach flexible enough to represent the patterns that you're interested in, and have you looked a little bit to see what works and what may not work, or just in general, what are your impressions about this approach?
So there is always an escape hatch because the matching part is PDL, and PDL lets you call them to C++, so you can write arbitrarily complex conditions. And there's also an escape hatch for transformations, because transformations are also implemented, like it's a C++ implementation of the interface. So you can have an arbitrarily complex matching in C++, and arbitrarily complex transformation also written in C++. So like you can do anything. It's not like there is a fixed set of transformations we are trying to design. There is a lot of trade-offs and design space on which transformations we should expose, and if you have this multi-versioning, how to, like, do you actually want to say, I am generating a multi-versioned code, so you have a transformation called create multi-version with multiple regions, each of which describes a particular version, or do you want to say, I just have my big multi-version saying that you implement in C++ and keeps doing what you are doing?
Yeah, no, I agree, obviously, but I mean, the role of this framework is to be as flexible as possible, in the sense that, I mean, clearly I can write everything in C++, and that's kind of what we do now. But if you have this framework, it would be really great to be able to apply, if you version for this one version, you apply those follow recipes. And so my question is more like, here you return ones and twos, and I'm not fully understanding what the specifics are, but do you think, and it's really an open question, so is that work well to basically be able to apply it to things we typically do for matrix multiply or really important code?
So I can try, like, if you give me a transform, like if you explain me what the transformation is in the forum, I can, for example, write and how I think the IR should look like for it. So I think it's flexible enough, and that's why I'm insisting, like, it's an interface. There is no predefined set of hops. I think there will be a common set of like combinators or like this control flow ops for transforms that we will come up with. But currently, I'm not proposing anything beyond like a simple sequence and try else, else, else. But we clearly can find, like we can find a transform multiversion like I proposed, or something else. But like I have not looked into much detail of what people need to be doing. But since it's MLIR, it's an open set of anything. Yeah, we can keep defining things. And basically, we would start by what we have and start saying, well, which of these things I want to materialize as IR for whatever reason. I want to generate it from a tool. I want people to meta-program it, so on. So yeah, I think it's flexible enough, basically, because there are enough of escape hatches, and it's MLIR, it's open, so it should be flexible enough. It's more a matter of how you encode these things than anything else. Like at this point, I think you can encode absolutely anything in MLIR.
Thank you.
Okay, I have somebody who's just called Alex with a 10 raised.
Hi, Alex. Can you hear me?
Not very loud, but yeah.
Oh, okay. Well, I'll try to speak up.
Yeah.
I just had a quick question. I noticed that in the example you're showing on the screen right now, you have X-form affine tile, and that means, in my perspective, that means that the affine tile operation is contained within X-form. Wouldn't it make more sense to put a transformation like affine tile within the affine dialect, and X-form calls the affine dialect's affine tile transformation? So that way X-form just depends on the dialects that have transformations, if that makes sense. Is that not possible?
It is possible. It would create some strange, so like currently there is an affine dialect and an affine transform library. So if we would do that, we would probably need to fuse those things into one library or do something. But that's exactly my question about layering. That's one of the options where we put these things in dialects and have each dialect depend on X-form or the other thing. So that is definitely a possibility. I just illustrated this as an example. So I really don't want X-form to depend on anything. Yeah, but like I don't have a good answer to this.
Thank you so much, Alex.
Sure.
We can probably do something like we do for passes, right? With some sort of registry exposed by X-form, and then that can be extended separately. I'm sure.
Yes,
I'm sure we'll figure out.
Yes, that is probably the direction, and yeah, I really want to figure that part out. Nicholas has a hand raised.
Yeah, it was more, I guess, response to the question that Alex Eichenberger asked earlier. So let's see. I would say there's a trade-off between basically the complexity of the matcher, the complexity of potentially an analysis or heuristic you would write in C++, and how much you want to chain these operations. So yes, I think there's multiple ways to write the type of transformations that you describe, like tile and permute and unroll jam and vectorize and peel and multiversion, etc., etc. But like details are really going to matter. And I would interject also that there's another angle of trade-off here, which is on what IR you apply that. And we've been also exploring like higher level IRs, and all these things that you mentioned are already kind of implemented in the lineage dialect and connect pretty nicely at that level. So what the best trade-off is, we don't know, but there's a pretty big space of trade-off.
Thank you.
Okay, River had more questions if we have time for this, or like I really want to get some kind of feedback on the layering. Yeah, Mahesh also has a question. So.
Yeah, sorry, I have a lot of questions, and I don't want to take all the time. One of the things that I wanted to see if this helps is all the evolution of the way linear transform have evolved through cogent strategy and cogent driver. Everything. One of the things that is fairly load bearing is the points at which you apply canonicalizations, because when you do a transformation, it requires the result IR typically needs some canonicalization that can be even not just related to that op, but also across the whole IR. For example, making the shape static or resolving tensor dim in dynamic cases so that you can remove tensor dim operations and some operations become dead. Things like that become really load bearing. And I'm wondering how you would inject things like canonicalization and CSE into like a sequence. You mentioned it in passing. I was just curious if you had more thoughts on it, but we don't have to spend time on it. You can either explain on the RFC. Or,
yeah, so I have a quick answer to that. So we experimented, and I think Jeff sent a PR some time ago, adding more listenable event to rewriters. So that could be sufficient. So when like canonicalizer is basically a greedy rewriter. So if you know that an operation has been replaced by another one, and if you get notified by that, you can update the mappings that you maintain. So there is some extensibility work that needs to happen, but yeah, we can basically, if we wanted to, we can run canonicalizations between every pair of transformations, and we can also scope them only to pieces we touched. Like there is also a design space there. It might need some more like feedback or a customized version of canonicalization. Okay, River, you had more questions or ideas? I know you do.
No worries. I mean, I'm technically on vacation right now, but we don't have to think about that. I guess some of the questions stem from what the expected uses are of this and how users intend to interact with this and how you see its place in like the ecosystem. Because one of the things that I mean, if we have like a per transformation dialect for every existing dialect, it starts to get very expansive throughout the entire ecosystem if everyone needs to define their own transformation dialect. So one of the things that I'm trying to understand is how you view this being used in, I guess, real compilation or production workloads, or if it's just a more of a research thing before you ship, because you mentioned how you package these transformations. I didn't know if you had a sense of you expect in a production pipeline to apply these specific transformations as part of like the actual workload or something else, because that kind of stems into a lot of the different questions I have in terms of layering or
yeah, I can try to answer that. So at the high, I see this as a way to control the top part of the code gen. So we have the bottom part with like lowerings and legalizations and simple like peephole transformations as I already have, but the higher level part of the code gen needs this kind of control. So I see that as it's a pass with a very like where this thing basically configures that pass. And I see this running in a compiler where basically we have some sort of, I don't know, a rather big set of transformation recipes controlled by patterns that can be updated separately from the main compiler. And then when we get a big program to optimize, we try to find the matching recipes for different parts of it from the database. So that's kind of the top level flow that I can see.
Okay, so you would view this as being applied in production pipelines through some database of recipes that I assume are found through search or something offline.
Yeah, either a search or written by experts if necessary.
Okay. Makes sense. I guess the other part of the question is how the interpreter itself is supposed to work. Because I mean, one of the things about registering these operations that isn't clear is that the interface of the interpreter is very important here, because that kind of ties in whether it's beneficial or not to actually represent these with operations and distinct dialects or not. If it's like the benefits that you get from that, but I guess you went over that a little bit. I mean, from a layering perspective, one of the things that's very apprehensive to me about this is the amount of dialects that would be created.
Yeah.
Basically, everyone needs their own dialect, and especially if this is something that's still being like, I mean, I assume this is not like you don't have a perfect idea of the perfect solution of the final state, and for something that is going to be like iteratively developed, one of the apprehensions I have is if we're just going to start like putting transformation dialects in every existing dialect, then it's still like we haven't achieved the goal of not being invasive because now we've invaded in everyone.
Yeah, I don't like that solution either. Like the problem is I don't like any of the solutions I thought of.
Yeah. So, I mean, that's the difficult part. So go ahead, Nicholas.
I guess I was just wondering, like, why not have an interface and then we could even have the operation name be an attribute for now, and xform.apply some operation name, and then that operation name is defined per dialect with just an interface. Or sorry, not per dialect. Per dialect, there's a bunch of transformations, and they just have an interface to hook up to the main xform.apply.
You mean
first step?
Sorry, go ahead.
Yeah, go ahead, River. You also proposed that on the forum.
Well, I mean, Nicholas, I guess the question is, do you mean like the affine dialect would have a tile operation that gets hooked in here? Because sorry,
right, it will have an operation because you need to hook up some IR entity to a transform to a C++ function that returns the handles. So that would be which would implement the interface.
Right. I mean, like there are various different trade-offs depending on it because you don't technically need an operation. All you really need is a named mapping between one thing and another, which operations give you that, I guess. But in some sense, like a native constraint in PDL is just a string mapping to a function that gets called, which is conceptually similar in a lot of ways. Given that all you're really doing is, I mean, because what this effectively boils down to, as far as I could tell, is you have an interpreter and the specific SCF.tile here is just injecting intrinsics into the interpreter so that the interpreter can continue executing or execute things that are external. And the model in which you define that injection is, I guess, what's being decided or discussed here. Because, I mean, defining operations is one mode of injection, but that also has caveats of, do we need in different dialects for every existing dialect, or do we want to inject into the transform dialect, which is conceptually possible? Or is it just like PDL rewrites where you're just registering functions with the interpreter itself directly?
Yeah,
Sorry,
go
ahead.
Like I see River proposed a similar thing, I think, to what Nicholas is saying. And yeah, at this point that could work. So we would need, like, we would basically need an interface that is equivalent to op definition. So we can inject the verifier and we can inject the logic for implementation, like for the actual transform. It still needs some sort of registration mechanism, like I think Mehdi mentioned before.
I mean, I think that's why Jeff suggested initially just extending the transform dialect, because you can technically register operations in another dialect. There's nothing stopping you from doing that except for exposing the API, I guess. But you can even define operations dynamically at runtime that can inject those different qualities, I guess. I mean, the different trade-offs here. And I don't have a perfect answer, especially because we're out of time, but one of the apprehensions here is that if the intention is for this to not be invasive, then we should ideally silo it-ish in some sense. But I think there are various different trade-offs there.
Okay, I think we are running out of time, but we can continue discussion offline or even online if necessary next time. Yeah, but yeah, please everybody think about layering this, and if you have any use or any idea, everything is helpful here. I don't think anybody has a perfect solution to this problem. And yeah, I kind of don't want this to be. I'm also fine if it is invasive, but I think it will take some time before it's fully ready to be used. So I want to minimize its invasiveness at this point.
So I'm unclear from what River proposed, whether there's also a suggestion that this could actually be done within PDL directly, or is that implied, or yeah, not necessarily implied.
Is River still around?
He hasn't
Sorry, I
left.
muted myself.
Okay.
I mean, I don't know if it would work right now, and I don't know what it would take, and maybe that's a good exercise, I guess, to just extend PDL to support some aspects of applying a chain of transformations. I don't know. But the scale there is also different in that if we want to be able to run passes and things from the rewrites, that's not something that patterns can do. As mentioned earlier, there's the listener aspect, which passes don't accept listeners. So we would have, I mean, that kind of goes into the questions about how the transformations are, like what kinds of transformations are allowed, because then you start placing restrictions on transformations. And if you place restrictions on transformations, then those restrictions feed into the transformations themselves. So if you have a listener and that's required, then now we need to push a listener through all of these transformations throughout the stack, and we get multiple ways that transformations get written with various different restrictions, which is difficult to justify in some sense.
So sorry, I was going to say that so far, at least, the transformations are mostly patterns, but the listener aspects are for some of the things that Mahesh mentioned, like there are normalization phases that are interleaved more or less implicitly for now. It's maybe more of an interleaving than a transformation itself that needs a listener. But that is probably just a point in time today. It may evolve, of course.
Yeah, I got to run, but should definitely follow up either on Discourse or online at another ODM or something.
Yeah, we're a bit out of time, but thanks everyone for joining today. Thanks, Alex. Great slides and very interesting topic. Let's follow up on Discourse. I think we're gonna
Thanks everyone.
answers for what's missing. Thanks everyone.
Yeah.